Okay, again, we're looking at the titration calculations. Diprotic weak acid plus strong base. Strong base like sodium hydroxide, potassium hydroxide, lithium, the group 1 hydroxides, or calcium strontium barium. If it's calcium strontium barium, then the stoichiometric ratios change over. Okay, so we have the amphoteric. The amphoteric is simultaneous, but we end up with a special equation. It's a pretty simple equation. That is, the pH is equal to the pKa for HA minus plus the pKa for the conjugate acid. The conjugate acid would be H2A, and that divided by 2. And so here, we don't have to do solution dilution. Step by is not necessary. In fact, in the buffer region, we technically don't have to do solution dilution. As long as we don't overly dilute the buffer, then the pH should be given by the Henderson also. But when we're at 0.3 here, we also don't have to do solution dilution because as long as the concentrations are fairly high, then this should be the pH. Now, what's fairly high is tricky to determine, but if it's like 0.1, that's considered high. All right, so once we start neutralizing this second hydrogen here, what we're going to have is we're going to have sodium HA or HA minus, either plus sodium hydroxide. This is going to yield Na2A plus water. In this region here, we keep the sodium hydroxide as the limiting reagent, the acid as the excess reagent. And so what we're going to have is we're going to have excess acid unreacted and then forms the product. And so when we look at this system, it's going to be the HA, A2 minus, HA minus, A2 minus buffer system. And so we call this buffer 2. This is buffer 1 here. Okay, once we've neutralized all of it, that is, we've added an equivalent amount of sodium hydroxide, we'll hit the equivalence point. The equivalence point is going to be twice the distance here. So if this were, let's say, 10 milliliters, the second one has to be 20 milliliters. That's not going to change. And so this will be 2 times. And so this would be the second equivalence point. So we call this the first equivalence point. This would be the second equivalence point. Yeah. Okay, then at the second equivalence point, we don't have an amphoteric. We just have Na2A. So Na2A consists of A2 minus. A2 minus is a dibasic base. Now, a dibasic base means there's going to be a KB1 and a KB2. This. KB1 and KB2. All right, and then once we, for the pH, though, typically we just give KB1, unless KB2 is significant. Most of the time it's not, and so KB1 is usually adequate. KW is not really necessary at this point. All right, then once we continue adding, there's going to be no reaction. So it's just going to be sodium hydroxide plus Na2A. And so this is the strong base, weak base mix. And so there's no reaction other than with Kb. So strong base, weak base, pH is usually dominated by the strong base here. So oftentimes we'll just ignore the weak base, unless the weak base is fairly strong. You can always do it, to be on the safe side, just do it like we did with the chapter 16 type problems. When we have a base mixture, we look for all the hydroxide ion producers. The hydroxide ion producers, the big one will be the strong base. The next biggest one will be the weak base, and this is a dibasic base. So Kb1, and then Kb2, and then Kw. And so we can do it stepwise. Yeah. All right, so we can take a look at. Okay, still recording. It did an automatic update. So the basic calculation is the same. And so you can do all titration problems exactly the same way. Exactly the same way as this is, calculation, the way I do it is step I. Your book is going to do it using millimoles, and then they're going to set the ice table using millimoles. You can do it that way, that's fine. If you take millimoles over milliliters of solution, then that's molarity. But I do it this way. I do solution dilution as my initial step. And then step one is the strongest acid plus the strongest base. So strongest acid plus base. And then step two is determine what's left over. And repeat step one. You know, this is a repeat. You take the strongest acid plus the strongest base. But sometimes you can save time. That is, let's say if you determine what's left over as a buffer, then you can go straight to the Henderson-Hasselbalch. You don't have to do the ice table for buffer solution. And so, and repeat, or etc. So we just take a look at what's left over. If you aren't certain if it is a buffer or not, then you can always do a standard route. Although this one will be tough. All right, so let's calculate some points here on the titration curve. Some common points that I'm going to show you the shortcut. First, we'll do a long method, and then we'll do a shortcut. Would be the half equivalence point. The half equivalence point is easy. The half equivalence point, we're going to have the pH is equal to the pKa. That's the half equivalence point. Then we have the 1/4 equivalence point. The 1/4 equivalence point, the pH is equal to the pKa minus 0.477. Let me check that really quick here. Okay, pause just for a second. Oh, I just have to step out. Okay, so yeah, it's the pKa minus 0.47. So I'll show you how to get the number really easily. We have another point here. It's called the 3/4 equivalence point. At the 3/4 equivalence point, the pH is equal to the pKa plus 0.477. Two more points that are very easy to get. One point is called the 1/11th equivalence point. So let's do that like this. Write it up here. The 1/11th equivalence point, which sounds weird, but the pH is really simple. The pH at this point is equal to pKa plus, or not plus, minus 1. And then we have the 10/11th equivalence point. At the 10/11th equivalence point, the pH is equal to the pKa plus 1. So, if the equivalent, let's say the first equivalence point came in at 10 milliliters, then the half equivalence point would be what? 5 milliliters, the 1/4 would be 2.5. The 1/11th would be 0.9, and the 10/11ths would be like 9.9. 9.09. And so let's do some calculations here for this particular acid. Actually, let me just do a generic calculation. So we're going to do calculations of the buffer 1 region. How do you know, first off, if you're in the buffer 1 region? How you know is you look, where the equivalence point is. So if you're between 0 and the first equivalence point, you're in the buffer region. That's how you know. So this is the first thing, is to recognize what region of the curve you're at. The next thing is we can do a calculation. So, example calculation. Let's titrate a diprotic acid. Like, what would be a good diprotic acid? Maybe the diprotic acid like oxalic acid. Oxalic acid is H2C2O4. Oxalate C2O4 2-. Oxalic acid is fairly strong weak acid. And then we're going to titrate this with 0.100 molar sodium hydroxide solution. Okay, the first thing is we need to know how much oxalic acid we have. And so typically we titrate with something like 25.00 milliliters. We normally have 4 sig figs here in the volume. Maybe 3 sig figs in the concentration, sometimes 4 sig figs in the concentration for more precise work. But if we take 25.00 milliliters of oxalic acid, and I'm going to keep the numbers simple. Your book, sometimes they'll keep the numbers a little bit more difficult. In this case, we can say this. To reach the first equivalence point would take how many milliliters of sodium hydroxide? Well, I need equal amounts of acid and base to hit the first equivalence point. Equal amounts would be, well, in this case, millimoles might be kind of useful. If I take milliliters and times it by molarity, I get millimoles. So this is 25 times 0.1 gives me 2.500 millimoles of acid. And so what that means is to hit the first equivalence point, I'm going to need 2.500 millimoles of base. And so how many milliliters would that be? Well, to get to 0.5, I take 25 milliliters times 0.1 gives me 2.5. And so I pick the numbers like this. I pick the concentrations the same. If the concentrations are the same, then I need the same amount. And so if I have 25 milliliters here, I'm going to need 25 milliliters there. Of course, that may be too easy. So on certain homework problems, they aren't going to have the concentrations the same. So they'll change the concentration. So for example, if this were 0.200 rather than 0.100, how many milliliters would it take? If this were 0.200, would it take double the amount of milliliters, or would it take half? It would take half because it's twice as concentrated. And so the equivalence point would come in at 12.5 milliliters. And so in this particular titration, we already know that the first equivalence point is going to come in at 25 milliliters here. And so this will be 25 milliliters. So as long as we're between 0 and 25, then that's in the buffer 1 region, and we could do the shortcut if we want. But first, before doing the shortcut, let's just do a long calculation. If I want a pH, let's say I don't want one of these points here. Let's say I want a point here or a point there. How could I get it? And so let's just do a general calculation here. So how many milliliters do you want to add? Well, maybe let's try adding 12.5 milliliters to this. At 12.5 milliliters, where would we be at? At the half equivalence point. So if we're at the half equivalence point, there's the shortcut, the short calculation. The pH is equal to the pKa. Or the long calc which we'll do here. Okay, the long calculations, all these calculations are the same, so we do step I. Solution dilution. And so when we do this, we're going to get a new volume. And the new volume is going to be 25 plus 12.5 is going to give me 37.50 milliliters. For titrations, we always go at least 2 decimal places. In fact, pretty much we just go 2 decimal places. So it's supposed to be a red speed. And then what I'm going to do is I'm going to figure out the new concentrations. And so the new concentration of sodium hydroxide is, okay, we added 12.5, and the final volume is 37.5. So it's a 12.5 to 37.5 dilution of 0.100 molar. So what does that calculate to? .5 divided by 37.5 times 0.1. And that gives me 0.0333 bar. Well, 366. So just repeat. Okay, so let's calculate the concentration of oxalic acid. Oxalic acid is H2C2O4, and that's going to be a 25 to 37.5 dilution, 0.100 molar. So 25 divided by 37.5 times 0.1 is 0.0666, and just repeat 6. Carry four digits there. Okay, so step I is solution dilution. And then the next step was taking the strongest acid with the strongest base. So we'll call this step 1. The strongest acid would be oxalic acid. And the strongest base would be sodium hydroxide. So I have my oxalic acid, C2O4 plus NaOH. Now, when we do this, we only neutralize one hydrogen at a time. Because the most acidic hydrogen would react. We wouldn't react the second one because it's a lot less acidic. The Ka for that is much, much smaller. And so this is going to form sodium hydrogen oxalate plus water. Still liquid. Okay, so initial oxalic acid after solution dilution is this. I'm just going to say quadruple 6.0. I'm not going to round, I don't round until the very end anyway. And then the sodium hydroxide is going to be 0.03333 molar. And the initial sodium hydrogen oxalate is 0 molar. And so this looks familiar. What's K for this? Well, K is this. We have a weak acid for a strong base. Strong always react to completion. Strong electrolytes, strong acids, strong bases, they always react. So K is very large. In fact, for this one, K is very, very large. Because strong bases react completely with water, which is a very weak acid. Oxalic acid is quite a bit stronger than water as far as acid goes. What's the limiting reagent here? Yeah, and so the sodium hydroxide is going to be completely consumed, but we're going to have excess acid. And so we're going to lose all of our sodium hydroxide. We're going to be left with 0.3333 molar, 0 molar, 0.0333 molar. Okay, now what we could do is we could take the strongest acid, which would be oxalic acid, and react it with the strongest base. The strongest base would be sodium hydrogen oxalate. You know, sodium hydrogen oxalate is amphoteric. It can act as an acid and it can act as a base. In this case, sodium hydrogen oxalate is both a better acid than water and a better base than water. And so that would be the reaction. But this is reacting an acid with its conjugate base. What are we going to form? We're going to form the same thing. There's going to be no reaction. We saw this scenario before, right? And so in that case, we'll take oxalic acid and react it with the next strongest base, which would be water, right? And that would be the Ka. And then we'll take the sodium hydrogen oxalate and react that with water. That would be the Kb, although this one has both a Ka and a Kb. So it complicates things. And so we end up with a whole bunch of equilibria, but what we should recognize is we have a weak acid and its conjugate base, which means we don't have to do all those ice tables. They're redundant. And therefore, we just use the HH. We don't even have to do an ice table. We'll just use the HH equation, Henderson-Hasselbalch equation. Well, if we use the Henderson-Hasselbalch equation, the pH is equal to the pKa plus, well, it's the pKa of what's the acid? The acid is going to be oxalic acid, H2C2O4, plus the log of the base. The base in this case, I'm going to get rid of the sodium ions. The sodium ions are spectators. They don't hydrolyze water, change the acidity. So this is HC2O4 minus over H2C2O4. All right, so this is just equal to the pKa plus the log of that ratio. The concentrations here are going to be 0.03333 over 0.03333, which is just 1. So the log base 10 of 1 is 0. So the pH is equal to the pKa at this point. And so we would just either look up the pKa or we calculate the pKa. The pKa here is going to be based on Ka1. This is pKa1 for oxalic acid, because it's Ka1 for oxalic acid. So this is the long calculation in this buffer region. Let me show you the short calculation for the buffer region. The shortcut calculation involves just looking at where we are in terms of the equivalence point. So let's just do it with what we just did there. The other way I would do this is like this. Let's do it for generic acid. I'm going to have some initial concentration, I'll just call C for my acid. And if I neutralize half of that, then that's 1/2 C. No, if I neutralize all of it, then it's C and C, the same concentration, same number of moles, and 0. This goes to completion. And so the limiting reagent is 1/2 C. And so I'm going to be left with 1/2 C, 0, and 1/2 C. And therefore, the pH is going to equal the pKa plus this, the log. Okay, so if I neutralize it, the base, 1/2 of the acid was converted into base. This is the base here. And then 1/2 of the acid remains. So this is the equivalence point here. Okay, this comes from C minus 1/2 here. Well, if it's 1/2 over 1/2, then 1. And the pH is going to equal the pKa at the half equivalence point. Okay. Well, what about, let's say, what about the 1/11th equivalence point? Let's check out the 1/11th equivalence point. We're going to do it the short way. This time I'm going to skip writing the ice table, and we're just going to go to the Henderson-Hasselbalch equation. Why? Because I know I'm in the buffer region, so I can use the Henderson-Hasselbalch. And I know the pH is going to equal the pKa plus the log. Okay, now this is going to be the 1/11th equivalence point. The 1/11th equivalence point means I've neutralized 1/11th of my original acid. And that 1/11th gets converted into base. And so, actually, did I get that right? Yeah. And so 1/11th gets converted into base. And if I converted 1/11th into base, how much do I have left over? I'm going to have 10/11ths left over. Does that make sense? Well, this is just going to equal the pKa plus the log. And so what I'm going to do is I'm just going to invert and multiply. And when I invert and multiply, I'm going to get the log of 1/10. The 11's canceled. Do you see that? And so what is the log base 10 of 1/10? Well, this is 10 to the minus 1. What's the power of 10 to the minus 1? This is the power function. What's the power of 10 to the minus 1? 1. Yeah, minus 1. Minus 1. And that's why we get pKa minus 1 here. So I just skipped the ice table, but you can kind of visualize the ice table if you need to figure this out. Okay, the next example we're going to do is we're going to do the 1/4 equivalence point. If I do the 1/4 equivalence point, the pH is equal to the pKa plus the base. So how much of the acid do we convert into base at the 1/4 equivalence point? Well, we've converted 1/4 of the acid into base, and that leaves how much acid unreacted? 3/4. And then what we do is we'll just invert and multiply or get rid of the 4s, and what we're going to get is pKa plus the log of 1/3. Well, what's the log of 1/3? The log of 1/3 is negative 0.477. And so this is equal to pKa minus 0.477. When I go to the next one here, the 3/4 equivalence point. If I'm at the 3/4 equivalence point, then basically I've neutralized 3/4. So the pH is equal to pKa plus the log of 3/4 over, and how much is going to be left unreacted? 1/4. So this is the log of 3 over 1, the inverse of that. And so let's just change the sign. So this is going to be pKa plus 0.477. And finally, at the 10/11th equivalence point, the pH is equal to the pKa plus the log. So we converted 10/11ths of the acid into base, and that means we have 1/11 left over. Invert and multiply, that comes out to the log of 10, or 10 to the first. 10 to the first would be 1, and so this is equal to pKa plus 1. Now, the thing that's missing here are the volumes. So let's figure out the volumes here. At the half equivalence point, remember, we have 25 milliliters here. So what's 1/2 of 25 milliliters? 12.5 milliliters. So this is going to be plus 12.5 milliliters of NaOH solution. At the 1/11th, what we have to do is we have to take 1/11th of 25 milliliters because the equivalence point is going to be 25. So if we neutralize this 1/11th, we're only 1/11th of the way there. And so what we need to do is we'll just take 25 divided by 11 parts. And so we'll divide this into 11 parts. And we get, so this is 2.27 milliliters. And so the 1/11th equivalence point is going to come in at plus 2.27 milliliters. For our titration that we're doing. You know, for other titrations, you know, this volume changes depending on what you have. What's 1/4? 1/4, so that would be half of 12.5, which would be what, 6.25? So this would be plus 6.25 milliliters of sodium hydroxide. The 3/4 would be 18.75. And the 10/11 would be 22.70 milliliters. Does that make sense? We're calculating the volumes of these. And so what we're going to do is pick any volume. What volume do you want to pick? As long as it's between 0 and 25, pick any volume. 17? Okay. So we can just take any volume and just repeat this, this style of calculation. So let's say plus 17.00 milliliters of NaOH. What is the pH at this point? And so the first step here is the equivalence point. What equivalence point is it? Well, what the equivalence point is we've neutralized 17.00 out of 25. So we call it the 17/25 equivalence point. Now, at the 17/25 equivalence point, well, that's going to cost us 17 milliliters. How much of the acid have we neutralized? So the pH is equal to pKa plus the log. Well, we've neutralized 17 parts out of 25 have been neutralized with that 17 milliliters of sodium hydroxide. So that's 17 out of 25 have been neutralized. That means how many is left over remaining? 8 out of 25. 8 parts out of 25 are left to go to hit the equivalence point. And so this is just going to equal to pKa plus the log of 17/8. So what is the log of 17/8? .327. So we're going to have the pKa plus 0.327. So we're just right here before the 3/4 equivalence point. Okay? All right. Now, what we need to know is also, what is the pH range of this? pH range is going to be from here to here. And so the amphoteric, let's figure out what the pH is at the equivalence point here. And make sure we're before the pH of the equivalence point. And so if we look at oxalic acid, which is on the bottom, actually not on the bottom, it's in the middle on the left. Do you see it? 5.9 times 10 to the minus 2. Is that correct? Yes. It's pretty strong. 5.9 times 10 to the minus 2. And so that's for oxalic acid here. So the pKa is going to be the negative log of the Ka, 5.9 times 10 to the minus 2. Okay, what does that equal? And so let's take the log of 5.9 times 10 to the minus 2. 1.229. That would be the pKa. Okay, plus the P. Oh, wait a minute. I did this backwards. That's all right. I did this backwards because I shouldn't have done I did the Ka for oxalic acid. That's the second term here. That would be this one. This one I'll do now because this one would be the Ka for hydrogen oxalate. The Ka for hydrogen oxalate is at the top right, 6.4 times 10 to the minus 5. And so this would be the negative log of 6.4 times 10 to the minus 5. 4.1938. 4.1938. 4.1938 plus 1.229 equals divided by 2. 2.7 divided by 2 comes out to 2.7114. A peak 2.7114 is really acidic. You know, that's about H3 right here. And so it just goes to show you the oxalic acid is very strong. This is why if you had oxalic acid as your unknown, a lot of people miss the first equivalence point because, you know, if you overly dilute the oxalic acid, you might start at a higher pH. You know, as you dilute things, the pH never goes down. The pH is just going to go up into the acid. And so this first blip might be pretty small. All right, so it's fairly low, 2.7. So pick any pH on this and we can figure out how many milliliters. Let's say pick a pH and let's figure out how many milliliters. That means the pH of oxalic acid itself must be fairly low. So let's pick a pH. Let's say how many milliliters will it take to get to pH 2.5? So we want to get a pH of 2.5. How many milliliters does that take? All right, so again, if we're at pH of 2.5, we're in buffer region 1. If we're in buffer region 1, this is why I calculated the equivalence point pH here, because I want to make sure I'm not in buffer region 2. You know, if I was in a pH of 3, I'm in buffer region 2. Calculation is going to be different. And so since I'm here, this is what I'm going to do. I'm just going to plug this into the Henderson-Hasselbalch equation and see what's missing. So I know what the pKa is. So what's missing is is the ratio. Okay, so let's go ahead. I'm going to get 2.50 is equal to pKa. Oh, I got these mixed up. This is 1.229. So at the half equivalence point, pH is 1.229, which is really pretty low. Plus the log of base to acid. What is called B over A. These have to be conjugated. It's not just any old base or any old acid that would work. So let's solve for the base to acid ratio. And so I'm going to get 2.50 minus 1.229 equals, okay, and then I'm going to take the anti-log of that. So I'm going to take anti-log of that answer. I'm going to get this. I'm going to get the base to acid ratio should be 18.664. All right. Now, what do I do with that? Okay, so I have my base to acid ratio. And so what I need to do is I need to figure out, I'm working backwards, I need to figure out what the equivalence point is. So if we look at here, here's a base to acid ratio, but this base to acid ratio is not the equivalence point. And so I have to figure out a way to go from here back up to here. And the way I go from here back up to here is look at this. I have 17 parts of base, 8 parts of acid. How many total parts is that? That's 25 parts total. And so I have 17 out of 25 parts base and 8 out of 25 parts of acid, where 25 is 17 plus 8. Okay, over here, what I'm going to do is I'm going to say I'm going to have 18.664 parts of base and 1 part of acid. How many total parts are there? And so what this is going to equal is it's going to equal 18.664 parts out of a total of 19.664. I just add them up because this is the total parts here. The total parts of base plus the total parts of acid will equal the total parts altogether. And the same thing we did over here. Now, that's how many parts of base I have. How many parts of acid do I have? Well, I only have 1 part of acid out of a total of 19.664. So do you see we're just going backwards here? Okay, now what the numerator is this is what we call the equivalence point. And so what I've done is I've neutralized 18.664 parts out of 19.664 parts total of the acid that was converted into base. So that's the equivalence point. And then in order to figure out how many milliliters, I'll take the equivalence point, 18.664 out of 19.664 times the total milliliters. The total milliliters to reach the equivalence point was 25.00 milliliters that we figured out before. And so this is the fraction. If I neutralize all of it, then it'd be 100%. And so 18.664 divided by 19.664 times 25, 23.728. Milliliters of sodium hydroxide. Okay, that should get us to a pH of 2.5. If I had time, I could double check this. How could I double check it? Well, I just reverse what I just did. Like we were doing earlier calculations.
This is for equivalent point 1.
Buffer region 1. This is for buffer region 1. Buffer region 2 is the same thing except it's offset. Because here we start at 25, 0 and end at 25. For buffer region 2, we start at 25 and end at 50. So calculating the volumes, we have to look at the 25. So the half equivalence point here would be 1/2 of 25, which would be 12.5. But the total volume would be 25 plus the 12.5, which gives us a total volume of 37.5. And so the half equivalence, this is 50 milliliters here. And it's not going to be half of 50 milliliters. It's going to be half of this second equivalent, which would be, yeah, so this is going to be at 37.5. So at 37.5 milliliters, what is the pH? The pH is equal to the pKa2. Okay, then we had the quarter equivalence point, which was 6.25 milliliters from the start being 25. So at the quarter equivalence point, it would be 6.25 plus 25, which would be 31.25 milliliters. That would be the quarter equivalence point. And that's based on this. From our starting point here, this is 6.25. This is 12.5. This is 25. And so we have to add the offset here, which is 25 milliliters. Does that make sense? And so in the second buffer region, there's an extra step that you have to do. The extra step that you have to do is just be aware of the offset as we start over again. We could calculate the 1/4. The 1/4 of the second equivalence point would be pKa minus 0.477. 3/4 would be pKa plus 0.477. The 1/11th, which would come at 27.27, I think it was, would be pKa minus 1, pKa2 minus 1, etc. You see that? Yeah. Or we could pick any volume. If we pick any volume, like pick a volume in that region, and let's do a calculation. We have to do an extra step. Between 25 and 50 milliliters. 42 milliliters, okay. So, at 42 milliliters, we know that we're in buffer region 2. And so in order to figure out the equivalence point, we're going to have to take our 42.00 and subtract the offset, because we're starting not at 0, we're starting at 25. And so that's going to give us, what does that give us, 17? $17.0 milliliters from the start. 0.00 milliliters from the start. This is the starting point here, 25. So if it's 17, then I've neutralized 17 out of 25. And so this is the 17 out of 25 equivalence point. And so the pH is equal to pKa plus the log of 1725. If I've neutralized 17 out of the 25, how much is left? 8 out of 25. So oddly enough, this is going to come out the same. At least for the correction, it's going to come out the same. The pKa is different. This is pKa2 now. So we're in buffer region 2. So this is the log of 17.8. All right. Likewise, we can pick any pH and figure out how many milliliters it would take to get there. So let's do that. But before we do that, I have to make sure I don't go into the excess base region. Go here, strong base, weak base mixture region. To do that, I need to figure out what the pH is at the second equivalence point. And so I want to figure out the second equivalence point now. And so this 4 is the buffer 2 region. 5 is the second equivalence point. 6 is the strong base, weak base region, or excess strong base region. So let's calculate the second equivalence point here, 5. So I'm going to have the salt, sodium oxalate. And when I look at oxalate, C2O42 minus, there's going to be a Kb1 and a Kb2. So let's first take a look at the Kb1 and Kb2s and then judge from those numbers if we need to do both of them or just one of them. All right, so let's first look at Kb1. So Kb1 for oxalate is equal to Kw divided by Ka for which acid? HC2O4 minus, did you say? Okay, that's correct. This would be the conjugate acid of this. All right, the Ka for that is 4.1959. Here it is, 6.4 times 10 to the minus 5. So this is 1.0 times 10 to the minus 14 divided by 6.4 times 10 to the minus 5. 1 times 10 to the negative 14 divided by 6.4 times 10 to the negative 5. 1.5625 times 10 to the minus 10. When you look at that, 10 to the minus 10, would you say it's pretty weak? I'd say it's pretty weak. In fact, I don't think Kb2 is going to be very significant. So Kb2 of oxalate is equal to Kb of hydrogen oxalate. It's just the weird nomenclature that we use. So the second step here would be hydrogen oxalate, picking up a hydrogen from water and making hydroxide. So if this is Kb for hydrogen oxalate, then that's going to equal Kw over the Ka for which acid? H2C2. Yeah, H2C2O4, that's correct. Yeah. And fortunately I didn't erase it because it's still here, 5.9 times 10 to the minus 2. So it's going to be Kw over 5.9, actually, just do the calculation. It's running out of room. 1 times 10 to the negative 14 divided by 5.9 times 10 to the minus 2. So the stronger the acid, the weaker the base. This is going to be 1.6949 times 10 to the minus 13. 10 to the minus 13 is just barely stronger than water. So this is not going to be significant. And so this will be, I'm just going to do Kb1 only. There's no point in going to Kb2, I think. Do you agree? It's 3 orders of magnitude smaller. And then it's like water. All right, that's good. That's going to save, because I don't want to do Kb1, Kb2, and Kw. You know, that would be 3 ice tables. So we'll just do 1. And so Kb1 is going to be C2O42 minus plus H2O, liquid. And so bases produce hydroxide. So we're going to form HC2O4 minus plus OH minus. Now, what is the initial concentration? Okay, except I can't use 0.1 molar here. It's not going to be 0.1 molar. Why? Yeah, one, we're adding, it was 0.1 molar. Originally, it was 0.1 molar, but we're adding more and more liquid. The more liquid we add, the more dilute things become. And so I skipped a step here. Now, what step did I skip? Yeah, I needed to go back and do solution dilution and then do this. In fact, I could do this the long way. I tried to skip a lot of steps here, because I already knew what was going to form. So this is the shortcut. The shortcut would be to take the millimoles. And in this case, the millimoles would be pretty convenient. Because how many millimoles did we have? 2.5 millimoles, and then 2.5, and at the very end, we're going to end up with 2.5 millimoles. And so the shortcut method here was 2.50 millimole over what's the total volume at the second equivalence point? 50 milliliters. And so what's that concentration come out to? So it's going to be 2.5 divided by 50, 0.05. 0.0500 molar. And then we just do a regular, this is chapter 16, basically. Now, it's easy to get all mixed up with this, especially if you don't have much experience doing these calculations. The more you do these, then the more you'll recognize them. But if you're not certain what to do, then you can always fall back and do the long method. And that's what we're going to do here next, etc. So this is the short calculation. And it involves, having to recognize certain things. But the long calculation is just kind of the same for all points in the titration. So let's look at the long calc. Second equivalence point. And so we started off with 25 milliliters of oxalic acid to 4 sig figs. To get to the second equivalence point, how many milliliters of base do I add? 50. And so this is going to be plus 50.00 milliliters of NaOH. And so the first step here is solution dilution. Solution dilution is 25 and 50 is going to give us a total of 75.00 milliliters of total solution. And so we need to calculate the new sodium hydroxide concentration here. The new sodium hydroxide concentration will be a 50 to 75 dilution. A 50 to 75 dilution of 0.100 molar, which is our original. Take that. So this comes out to 0.06. We'll go quadruple 6, and it just repeats molar. Okay, now we're going to do the oxalic acid. Oxalic acid is half as much, the same concentration, so it's 25 to 75 dilution, 0.100 molar. Which is going to give us 0.0333. We'll do quadruple 3 molar. So that's our step I. And then we go to step 1. Take the strongest acid, which is oxalic acid, and react it with the strongest base, which is sodium hydroxide. This is going to form sodium hydrogen oxalate plus water. And then we plug it in here. The oxalic acid is 0.0 quadruple 3. The sodium hydroxide is 0.0 quadruple 6. This is 0, and water we ignore. All right, what's the limiting reagent here? Yeah, the oxalic acid is the limiting reagent. We're going to completely continue that. And so, see, we'll be left with 0 molar here. I'm going to skip some steps here to save time. This is going to be 0.0 quadruple 3 molar. This is going to be 0.0 quadruple 3 molar. And so here I'm left with base and hydrogen oxalate. Hydrogen oxalate is an amphoteric species, so it would be an acid. So is this a buffer? I have base and acid. This is not a buffer. One, you'll never have a strong base or a strong acid in a buffer. It's got to be weak. And 2, they have to be conjugates. These are unrelated. And so this is not a buffer. So we can't do the Henderson-Hasselbalch. If we can't do the Henderson-Hasselbalch, where do we go from here? We'll just repeat. The repeat is we'll take the strongest acid that remains. What is the strongest acid that remains? Yeah, sodium hydrogen oxalate is going to be stronger than water. So this is going to be our step 2. Take the strongest acid remaining, sodium hydrogen oxalate, and react it with the strongest base. The strongest base is when we have excess sodium hydroxide left over. And so this is going to give us sodium oxalate and water. All right. As always, strong reacts to completion. K is very, very large here. And the same thing here. K is still very, very large because we still have strong base left. And so this is going to react to completion. But when we look at this, what's the limiting reagent here? Yeah, there's no limiting reagent. This is what we call stoichiometric. It's stoichiometric. It's just the right amount. We call it, equivalent amounts of acid and base, which is going to get us to the first point. So this is going to be 0 molar, and we're going to be left with 0.03333 molar sodium oxalate. Okay, now after step 2, we look at what's left over. Do we have a Henderson-Hasselbalch buffer left over? No, because we have the base, we don't have the acid. And so this is not Henderson-Hasselbalch. So if it's not Henderson-Hasselbalch, then what we're going to do is we're going to just take the strongest acid and react it with the strongest base. So I don't have any acid here. And so I have to use water. And the strongest base will be sodium oxalate. And so this will be my step 3. My step 3 will be just oxalate, sodium oxalate. Or I could just do oxalate. I can get rid of the sodiums. And water. This is KB1. So KB1 is going to produce sodium hydrogen oxalate and sodium hydroxide. I probably should have just done it now. C2O4 2 minus plus H2O liquid. Get rid of the sodium because sodium is just a speck here. Gives us HC2O4 minus plus OH minus. That's KB1. What's the initial concentration? The initial concentration is 0.0 triple quadruple 3 molar. That's the same concentration we got for the shortcut method, I think. It was 8 out of, what was it? 8 out of 27, which is 1/3. Or is it 1/3? I don't know. Yeah, 24. So this is the long method. We do the Kb, we figure out how much hydroxide. From the hydroxide, we'll get the POH. From the POH, we get the pH.
I'm a little confused when you're doing step 3. It's just the reverse of step 2.
Step 3 is the reverse of step 2, but the thing is this. When we make this assumption here that strong reacts to completion, that is technically not accurate. In other words, if K is very large, I said K is very large here. Right? K is very, very large. So let's check our equilibrium concentrations. Is this an equilibrium? So when we check our K here, it's going to be 0.03333 divided by 0, divided by 0. It's infinite. So when I check my K goes to infinity. Well, is very, very large the same as infinity? No. And so technically it's not. The reason why we do this, there are numbers for this. Back in chapter 16, they gave you the number for HI, the Ka, rather than saying the K is very large. The reason we do this way is because if we do this way, what we can do is, this is called resetting. This is resetting without having to reset. So if we stopped here at step 2, I would have reset this. Because the K in this direction is huge, the K in the reverse direction is small. If I didn't reset this and I plugged this into my calculator using the actual K value here, the calculator would have rounded it to 0.03333, and then I would have ended up with 0, 0, and it wouldn't be an equilibrium. And so this is the fix, in a way, for this. Now, this is the reverse. Now we're figuring out how it re-equilibrates. And so do you see what they're doing here? What they're doing is they're resetting and then letting it re-equilibrate. Does that make sense? Make sense? Somewhat? No?
It just seems like it's going to go back and forth.
No. Once you're done with this, then it's over. What is the KB for this? Well, we have a number for the KB for this. We calculated it. Didn't we just calculate the KB?
1.69 times 10 to the negative, or it's 1.6949 times 10 to the negative 13.
Times 10 to the negative 13. This is the KB. Actually, I want KB1. Was that KB1? I need. What was it?
1.5625 times 10 to the negative 10.
Okay. Okay, this is my KB1. Okay, now we go back to this. What's the K? I said the K is very large, but what is really the K value for this equation?
KB2.
No. It's going to be, this K that's very large is 1 over, remember when we reverse the equation, we invert the K. And so it's going to be 1 over 1.5625 times 10 to the minus 10. So we could have stopped here at step 2, used this K value, and then calculated equilibrium. And what we'd end up with is just the exact same equilibrium concentration. So if I had stopped here and actually used the K value, I would have gotten the same equilibrium as I would have at the end of step 3. The reason I didn't do that is because this is just resetting the equilibrium. That's all we're doing is resetting it. You see? The other reason I didn't do it is because if you have too many variations of things, as long as you can keep all the variations of all the problems clear, it's like, you're trying to learn, let's say, a jungle, but there are thousands of paths in the jungle. Do you try to learn every single path? No, what you'll do is you'll just do the same thing, and then slowly add on paths to that. And so if we do it the same way, then we won't get it messed up. In reality, though, we're doing this stepwise. In reality, we should be doing these simultaneously, because that leaves a problem with this. There should be some residual oxalic acid left over, which we are ignoring. Okay. So what is the pH at the equivalence point? Well, the pH at the second equivalence point, we can calculate based on just KB1, and that's going to be fairly high. And then for the excess base region, we could do a shortcut method, figuring out how many millimoles of sodium hydroxide would go in reactant. Or we could just do it the long method. The long method, we just keep doing the same. Strong reacts to completion. When you get to the final point here, you know, the strongest base present would be sodium hydroxide. The strongest acid present would be water. So sodium hydroxide and water just is hydroxide. And that would be the pOH. And then we get the pH. And so on. So anyway, the long method, we always do it the same. Strong reacts to completion, and then let it equilibrate at the end. Okay. Are we out of time? We have more time. 4 minutes.
Second equivalent point pH. You said based on the first equivalent point pH, but we just do a second equivalent point pH.
Well, actually, the second equivalence point pH, we can do it here. I ran out of room here, so that's why I stopped. But the change is going to be minus x, 0, plus x, 0, plus x. And so I'm going to use the simplifying assumption for this because it's so small, 10 to the minus 10. And so I'm going to simplify 0.0333 minus x just to 0.0333. And so that's going to be this KB1. So it's going to be 1.5625 times 10 to the minus 10 times 0.03333 equals, and then I'm going to take the square root of that answer. And so this is going to give me a hydroxide concentration, or X, equal to 2.2821 times 10 to the minus 6. 2.2821 times 10 to the minus 6, I might start worrying about Kw, but let's not worry about it now. Like 10 to the minus 7, 10 to the minus 8, I would worry about it, but here I'm not. And so I'm just going to do the log of that answer, which is going to give me a pOH of 5.6417. I'm not going to worry about Kw, it's not going to do anything, which is going to give me a pH of 8.3583. And so the pH at the second equivalence point would be 8.3583, which is fairly basic. So the first equivalence point was acidic, 2.7. The second equivalence point was quite basic, here at 8. Like I said, we can do all the calculations here on the titration curve using the long method. You know, it's just the shortcuts can help you save a lot of time if you want to use those. Okay, and then the pH is just going to climb. The pH flattens out here because of solution dilution. You know, at infinite dilution, well, it's not really dilution because we're adding 0.100 molar sodium hydroxide, so the pH should hit 13 eventually, but it would take a lot to get it to hit 13. All right, so we're just about, I'm not going to start a new calculation.